It's a privilege and an honor to moderate this session called The Next Golden Age of Astronomy and to introduce our three speakers. The title, The Next Golden Age, of course, raises immediately the question, what's the first golden age? All of you who are astronomers here for sure know that we do live in a golden age of astronomy, in part and in no small part due to our Great Observatories program. Each of our speakers here today has invested a portion of their career in NASA's astrophysics missions and facilities, and each has committed towards bringing about the next. They are ushering in our future. And to give you a hint about how exciting that future might be, if you look at the slide there, that picture of that planet, that's not the Earth. Okay. I would like to mention up front that I am indebted to Jason Callery for helping me with this presentation. The eye candy is entirely due to Jason. Okay, NASA's legacy, the Great Observatories. The Great Observatories are fundamentally connected to what we call the decadal surveys. The decadal surveys are a rigorous scientific process by which the science programs were created. The decadal surveys define the most important scientific questions of the decade, and from these emerged the Great Observatories. Let's take a look. Oh, I'm sorry, I haven't gone there yet. Let's take a look at what we see here. First Great Observatory was the Compton Gamma Ray Observatory, issuing from the 1980s, followed by the Chandra X-ray Observatory, a different wavelength yet, followed by the Hubble Space Telescope, identified at that time as UV optical, and then followed by Chandra in X-ray. The next decadal survey comes the Spitzer Space Telescope for infrared. By now we have 4 major facilities operating across wave bands and largely overlapping in their operations phases, all very important. They have and still continue to provide groundbreaking science. And I am sure as we move to the next decadal, through which James Webb Space Telescope was originated, and the following for WFIRST, we expect to see the same groundbreaking science. Great observatories actually are not simply United States constructs, actually. We have international partners. Although I will be somewhat US-centric and NASA-centric in my discussion, I want to say right up front, there are international partners that have worked with us and to enable these facilities and this amazing science. Among them, ESA and the Canadian Space Agency specifically. Okay, now the model for space observatories such as this is interesting in the following sense. I was an instrumentalist. I helped to prepare instruments for Chandra X-ray Observatory. And so I know all the inner secrets of a particular instrument and the magic that you have to do and the dance to make the instrument perfect. But what's important about facility class instruments of great observatories is that what you need to use it is not insider knowledge. It is not black belt expertise on the hardware. It's a good idea and a successful proposal. The Great Observatories model leverages off 3 very important aspects that have been provided by NASA. The first is that the Science Operations Center worked to enable ease of use. If you have a good idea, you can use this observatory successfully. The second, NASA also funds analysis of the data so that they don't lie dormant waiting for analysis to happen. The science is returned, hitting the street almost immediately. And third, NASA has committed to maintaining these archives. We now find that more than half the productivity of Hubble comes from using the archives, so that this is a gift that keeps on giving. What's interesting about this, I have chosen a selection of Hubble images down below. In the upper left, for example, is Jupiter with 3 moons and their shadows. And on the right is the Einstein cross of a supernova observed through gravitational lensing in the frontier fields example, which is just a very recent iteration of use of discretionary time by the director. Now, what is interesting is that here we have a 25-year-old observatory that is returning groundbreaking science today. That is true for all our great observatories and is enabled by this structure. Notice the remarks that are in the corner there. You have diverse community engagement. You have diverse set of questions that can be answered because it is a broad facility. Competition creates creativity. You have long-term discovery potential, which goes on even with archives, and you can exercise synergy with future facilities. In the last proposal call for Hubble, 11,000 proposers were engaged in that. You should know that 11,000 is about the number of the entire registration of the International Astronomical Union. All right. Now, what are our next steps? That's the present. Our next steps, we see here, we have Hubble. What would be the next obvious step past Hubble? Well, obviously, the first thing you want to do is you want to go for more power, and James Webb provides that. The next thing you would consider doing is to go for wider area, and WFIRST provides that. We have several speakers here who will speak on James Webb. I just want to turn to WFIRST as an example. Consider the Hubble Ultra Deep Field shown here. Basically 10,000 galaxies, a few, very few, high redshift, meaning that they are exhibiting light from the very first few years after the Big Bang, first few million if you like, 100 million perhaps. But the point is, you have 10,000 galaxies and one or two perhaps very high redshift objects representing early universe objects, very powerful, very paradigm-changing observation. What will WFIRST do for us? Here's the Hubble Ultra Deep Field. This is the same observation with WFIRST, quite literally 100 times larger. You now have 1 million galaxies and 100 high redshift objects instead of just one. For those of you who have a deep field picture behind your desk at work, you're going to need wallpaper. And so where do we go from here? We talked about the now and the near term, but what's next? What's the next golden age? Well, NASA has brought together about 30 of their brightest young astronomers and astrophysicists to talk about what are the next visionary ideas. And they have created this drawing, illustrated here is Enduring Quests, Daring Visions, effectively a roadmap for the future that would map out what the next steps are likely to be or should be based on our knowledge now and our interest in what lies ahead. So the idea is to lay out a compelling vision for NASA astrophysics that would last us 30 years. I encourage everyone to look at the document, but I want to talk about the eras that are represented to the right. The first thing not shown here is what's going on in present day, all right? This begins with the near term. In particular, the near term includes JWST, which we can talk about, WFIRST, which we have mentioned just now, TESS, which I think will come up briefly in some of our later discussions. These near-term missions were considered givens, if you like, were considered already committed, and the document attempted to look at the era farther out. So I would like to take your attention to what is called the formative stage. This stage includes gravitational wave astronomy, and I would like to apologize to Joan Centrella, who's sitting here. We probably will not be able to cover that in this session, but we will talk a little bit about the others. Gravitational wave astronomy is an important messenger of information included in this suite of tools. We have several others, and they may look familiar to you. They are all going to be revolutionary, and they will provide transformative capabilities. An example, for example, is this large UV optical infrared surveyor. When we say large, 10 meters or greater, it would be able to detect biomarkers and evidence of life in other Earth-like worlds. Indeed, it is likely to be able to see the seasons change on an exoplanet. So what does this roadmap look like? Well, effectively, it breaks down, as you see here, into the scientifically interested goals or questions, and what suite of missions would be able to weigh in and provide information on those various goals. These missions are listed as current, near-term, if you like, the formative stage, which I'm calling now the Great Observatories 2.0. And if that's not visionary enough, then there's even beyond that, visionary stage. But the rubric of all of these visions really condensed down to three simple questions. three themes which are the pillars of astrophysics. The first is, how does our universe work? The second here, how did we get here? And the third, are we alone? Those three simple questions can more or less sum up the investigations that are laid out in this exciting plan. The speakers today actually represent expertise in all three of these particular pillars. John Mather will be our first speaker, Mark Clampin our second, and Alexey Vikhlinin our third. I would like to suggest that we save our questions until we get into the discussion period. That's it for now. Thanks. That's it, John. I'm going to introduce. Now, I would like to introduce our first speaker, John Mather. Many of you know him. Dr. John Mather is a senior astrophysicist in the Observational Cosmology Laboratory at NASA Goddard Space Flight Center and the senior project scientist on the James Webb Space Telescope. His research centers on infrared astronomy and cosmology. As an NRC postdoctoral fellow at the Goddard Institute for Space Studies in New York City, he led the proposal efforts for the Cosmic Background Explorer, COBE, and came to Goddard to become the COBE study scientist and later on its project scientist. John was also the principal investigator for the Far Infrared Absolute Spectrometer, FIRAS, on COBE. He has received many awards for his precise measurements of the cosmic microwave background radiation using the COBE satellite, among them the Nobel Prize in Physics in 2006.
Well, thank you, Kathy. I think before proceeding, I wanted to say that a Nobel Prize really represents a community effort. When we got to go to Stockholm, we took as many members of the science team as we could, and a tiny fraction of the well over 1,000 engineers and technicians and many other people that helped make that project happen. So all of these things that we do are social projects. People think sometimes that scientists are loners. Well, this is the most social thing you can possibly imagine being in. So I want to tell you something about what we have in mind for the James Webb Space Telescope, and our heading here includes pointing out that we're doing it on behalf of the 7 billion people that live here on Earth, about 10,000 future observers, because that's about how many have already used the Hubble data, and there are about 1,000 engineers and technicians currently working more or less full-time on the project, and that doesn't count all the others who are part-time or did already work on it. Our project has been going a long time, as most of you know, and representing 3 space agencies. So it's going to be a pretty amazing thing when it flies. I want to show you just a few of the things that it could do and will do for us. So this is a summary chart, which many of you have seen many times. It says basically this is an international partnership that NASA is leading, and we are leading it from Goddard Space Flight Center right around the corner. This telescope is huge. It's 6.5 meters, about 21 feet, so it's roughly floor to ceiling in this room, just to get the mirror here. And the mirror is larger than the rocket, so there's a wonderful deployment process that happens later. We have a partnership also for the instrumentation. Instruments come from the United States, Canada, and Europe, and all of them are finished and have been tested at Goddard. In fact, we've recently finished the second cryovac cycle on them. So doing well on putting it together. The observatory will be run from the Space Telescope Science Institute, where Kathy is, just as we run the Hubble Space Telescope. We're updating some of the software, of course, converting things to Python, which I have never read, but people tell me it's the best language. So we're getting ready. Astronomers are getting ready, and I'll show you at the end that we're even having a user training workshop coming for them. The observatory is aimed for infrared astronomy, and so why would you want to do infrared astronomy? Well, number one, it's the next scientific frontier. With the Hubble observations, we saw that we couldn't see far enough to see the first galaxies. We couldn't see inside the dust clouds where stars are being born, and both of those are answered by having infrared light and picking up infrared light. So it's the natural successor scientifically for Hubble, and it, however, leads us to this remarkable design, which is completely different from what we have for Hubble. So we will be launching it in about October 2018 to the Sun-Earth Lagrange point, which is 1 million miles from here, overhead at midnight. So it's not, we don't exactly go to the L2 point, we orbit around it. Anyway, we'll be going there, and it'll be not so far off into the future. So what else do we say here? We are carrying fuel for 10 years of observational life. Fuel is needed because the orbit's unstable, and also the sun tries to push the telescope and turn it over, and we have to fight that with fuel. So there it is. Just imagine this thing enormous. The sun shield, that purple thing in this picture, is actually a piece of plastic about as big as a tennis court, and so it's maybe longer than this room, but maybe not quite as wide. Anyway, it's enormous. That's a pretty enormous engineering challenge. I'll show you what we're doing about that. So if this works, I am showing you now a movie of the formation of the universe. This is a 3D simulation showing the motion of particles as pulled together by gravity. This is something we could not do until quite recently. We have powerful enough computers, and based on the measurements made with Cosmic Background Explorer, with the WMAP and the Planck, we now think we know more or less what the initial conditions of the universe were like. So we can say, okay, universe, here's your starting conditions, go. And so this is what the computer tells us happens. First happens is dark matter pulls itself together into clouds. Then the dark matter attracts ordinary matter and makes it light up into galaxies. And this is over the course of, what is it saying, several billion years. The structure gradually changes from something that starts very nearly perfectly uniform, something that's extremely stringy. Galaxies are spread out in amazing structures, which we can actually see in the sky. At this point in the movie, you see things are beginning to explode. This is active galactic nuclei turning on and liberating immense amounts of energy. Also, stars start to blow up, supernovae explode, and material is enriched with the chemical elements of life. So we're here because of that stuff. And by the way, we wouldn't be here without the dark matter, which is necessary to cause the galaxies to form, and we wouldn't be here without all those explosions that liberate the elements of life. So here in the universe is getting on towards about the time the solar system is formed, when the solar universe is about 9 billion years old. Solar system forms. Our material has been recycled, probably assembled from about 1,000 different supernovae that exploded, and our material has been probably out of the galaxy and fallen back in. So when you look in the mirror in the morning, think cosmology. So here it begins to settle down. According to simulations, the universe becomes more and more peaceful. Stars are formed less frequently, but material is still falling together under the force of gravity. So now you say, well, that's a wonderful movie. Is it true? Well, it sort of matches the structures that we see in that beautiful photograph that everybody loves from the Hubble Deep Field, but it's tricky to make the detailed comparison, and we argue about whether it's right. So we're not ready to tell you that. If you ask the supercomputer people, when are you going to tell us the right answer before we take the picture, they say we can't. So observational astronomy, that's the key of all of this. We have been surprised over and over and over, and that's why we build telescopes. We cannot do it by the computer. So we're very proud of the computer, but the question that we now have to answer from observations is, does that program match reality? So here is another reason we need to build a telescope that sees infrared. This is a picture taken by Hubble of a newish star being formed in a bright cloud of material. It glows beautifully. It's being lit up by bright stars. And you can see this amazing structure. It doesn't look anything like a star. And if you could take a picture with the infrared capability of Hubble, you can begin to see through the dust. So there it is, the same object. Most of the dust went away. And you can now see that there's a star in the middle, spurting out jets of material from its two poles. As it's probably also forming a disk of material in there, probably forming a planetary set right around that new star. So infrared lets you look inside to see the mysteries of formation of stars and planets. So a very cool reason to have an infrared telescope. Cool, by the way, also refers to the temperature of the things that we can see. The stars that you see with your eye are thousands of degrees Kelvin or centigrade or Fahrenheit. the things that we can see with the telescope can be a lot colder, even down well below room temperature. We can still pick them up because that's what infrared lets us do. So one thing that Mark will tell you more about is the ability to study planets around other stars. When a planet goes in front of its star, some starlight goes through the planetary atmosphere on its way to the telescope. We will be able to analyze that, and Mark will tell you much more about how we do that. But it's a capability the Webb telescope has that we did not originally plan for. In '92, the first planet was discovered, but we thought, well, we'll never see those. Then it was discovered that they're very common and that we know how to find them with the Kepler Observatory and various other techniques. So now we know more or less when and where to look to see this happen. So we will definitely be trying this out. So now what have I got next for you? Try this. This is a picture showing how the telescope folds up to fit in the top of the rocket. It is a snug fit. Some of you remember we were going to have an 8-meter telescope. I don't quite know how we would have fit it in there. So we're happy with 6.5 meters, and it's still extremely powerful. The picture on the upper left shows you a side view. There's a 5-layer sun shield, which is, like I said, as big as a tennis court. The sun is in the lower side. The telescope is always in the dark and is therefore able to cool down to a temperature of about 40 Kelvin. And so do the instruments. Inside there is a single instrument that requires 6 Kelvin of cooling, and we have an active refrigerator to do that using gaseous helium. So there it is. Now I want to show you the next, if this thing will properly do the right thing. Oh, this is a sketch of the optical configuration. It's a Cassegrain telescope, augmented by a more complex mirror system behind to improve the optical quality. It's called a 3-mirror anastigmat. And the picture illustrates that we have 18 hexagonal mirrors, all operated to and adjusted to function as a single large hexagon, and they all have to be polished up to be the right shape when they're at the low temperature. So we figured out how to do that, and these are all extremely lightweight. They're all finished, and they are in the storage containers over at Goddard. Not going into much detail, here is our movie of the deployment. This is the short version. The first thing that we have to do after launch is get solar power. We unfold the solar cells, then the telemetry dish comes out. Then over the next couple of weeks, the rest of this happens. We unfold the sun shield in 2 parts. Then we unroll its covers. Separate the telescope from the warm spacecraft bus. It's all done by remarkable mechanical devices, all done by remote control from here. We send up individual commands when it's time to do each of these events, and before we send the next one, we confirm that each one has worked properly. You might say, isn't that pretty complicated? The answer is yes, but we asked our contractor, isn't that the most complicated thing you ever did? And they said, definitely not. But it's in the top 5. So we know that we have a methodology to do this, but nevertheless it's tricky. We have to work very hard and test and rehearse and test and rehearse and examine the design and make sure, among other things, that there are 2 of everything where you could. So every motor has 2 windings, every controller, every winding has its own electrical controller on each winding. So where you could, you do have 2 of everything. So that's what it takes to get this thing up and working. The last step is it has to cool down to the operating temperature and then get focused. From the Hubble telescope, we learned how to focus after launch, and we do that on purpose. So that's the unfolding. Now we will demonstrate that we know how to do this. This is a laboratory unfolding of the sun shield itself. So here you see the motors pulling out the sun shield. The people are there to make sure nothing snags, because there's a difference between 1G and 0G, and making sure that we're watching everything that could go wrong in the process, and we'll catch every mistake. So this took place over a couple of days, as I recall, and the next one that we do, the final one, has to be done without all those people because it's got to be clean. So you see that it pulls out in stages. First we pull out the booms sideways. Then after that's all finished and we've checked it all out and photographed it, Then we will pull on additional cables and we'll separate the 5 layers of the sun shield. And 5 layers, by the way, are required so that it'll keep the telescope cold enough, even if there are holes in the sun shield due to micrometeorites and other unpleasant surprises. So here we're pulling on the cables and separating the layers. There we go. So I think I've shown you why this is hard. But also that we now know what to do. So we have another one. This one happened right over here in our shop. This is the big clean room at Goddard Space Flight Center, and here we are unfolding the telescope backplane pathfinder structure. So you see the secondary mirror tower being lifted up. And of course we have to negate gravity one way or another here. Lots of help is required in 1G when you want to simulate 0G. But anyway, we got it to go up, and we're happy with that one too. So this particular system has now been shipped down to Johnson Space Flight Center, where it is being used to set up the optical tests that we will be doing there after we get our whole telescope put together here. Also difficult, but completed. Eventually, this all has to get folded up to be shipped to Johnson Space Flight Center. I'll show you the next step after this movie is over. See if this will do it. That's the next step. Put it in the truck, drive it around the Capitol Beltway in the dark, drive it onto the C-5 aircraft, and fly it down to Houston, and then undo it when you get there. So that shipping container just barely fits under the bridge, just barely fits into the airplane, but it's just what we need. So this is what we're going to do at Johnson. This is the chamber A there, which was used by the Apollo astronauts to rehearse getting out of their capsule into a vacuum. We made it different. We made it cooler. This telescope will be cooled down to the operating temperature in this big tank. There is test equipment at the top, and there is the telescope at the bottom. And this is all set up and getting prepared to go. We've got to prove the test equipment before we can put the flight hardware in there. But anyway, that's the next step after Goddard. And now, just to wrap up, this is what you want to know if you're going to observe with the observatory. We have published lots of documents about the science that people think they would like to do, the capabilities of the observatory, various scientific white papers where we outline what we think we should do. And there is an archive of a last conference that we had, so information is available. Next, coming up, we have a workshop at Space Telescope Science Institute for future users. It's only May, so it's just a few months off, a couple months, right? So anyway, time to register. If your young friends or older friends want to be able to use the observatory, this is how. In October, we're having a scientific conference at STEC. So I think I put a slide about questions, but we're going to defer the questions, right? So, okay, thanks very much. We'll do the next.
Our next speaker is Mark Clampin. Dr. Mark Clampin is James Webb Space Telescope Observatory Project Scientist at Goddard. Prior to joining the JWST project, Mark was a member of the science staff at the Space Telescope Science Institute, where he served first as the instrument scientist for WFPIC-2, followed by STIS, and then as the Advanced Camera for Surveys group manager from its inception to the completion of orbital verification of the instrument. Mark was a co-investigator of the Advanced Camera for Surveys with responsibility for the focal planes and is a co-investigator for the Transiting Exoplanets survey satellite tests.
Thank you. It's a great pleasure to be here. I should just say I was actually in the clean room during the video John showed you of the sun shield deploying, and I've never seen so many film crews in a clean room in my life. So I think we've really entered the age of Hollywood astronomy here. So I'm going to talk about a couple of missions that address this question of what's next, primarily focused on UV optical to the near infrared. You've already heard about the first of those, which is WFIRST. And WFIRST, also known as AFTA, basically uses a telescope that was provided to NASA by one of the other government agencies, and is primarily designed to address the question of dark energy. So it will undertake a number of really groundbreaking investigations using this enormous wide field capability. I think Kathy's just coined the name wallpaper telescope here. But it will be able to do a number of surveys that do different kinds of standard candle and standard distance measurement, and also weak lensing that allow us to map out dark matter clustering in the early universe. And that wide field capability is what we need to be able to do that. It also does a number of other things. It will allow us to do a statistical census of planets using the technique of microlensing, which is using gravitational lensing to detect planets. Now, you detect them, the event finishes, and you can never go back and follow them up because most of them are quite a ways away. But it allows us to complement the data that we've got from Kepler and really extend our knowledge about the statistics of exoplanets and the occurrence of different mass ranges, that outer edge of the solar system, basically from the sort of orbit of Mars out to larger distances. So it's a very powerful capability that will completely fill in our understanding of the statistics of exoplanets. And then WFIRST also has a new capability, which is a coronagraph, and this is a technique that I'm going to be talking about quite a bit that is used to characterize and image planets around relatively nearby stars. And what WFIRST will do is undertake a survey of planets that we already know exist from radio velocity surveys on the ground, where we've measured the Doppler shift due to those planets. And it should be able to do a few tens of these planets really well. It's also a 2.4 meter telescope like Hubble, has a much wider area, and so it will also provide a vast legacy of major survey science that can be used by the community. You heard from Kathy that the HST archive is now a major resource that's heavily used by the astronomical community, and you can only imagine how that's going to expand with WFIRST taking these massive, very deep wide field images. And it will also be able to do pointed observations for some fraction of the geo community. So I just put these two images in here. One you've already seen, which is how big this field of view is. It is just enormous. And these two white boxes here show you the two major HST imaging fields of view, the wide field in ACS and the wide field in wide field 3. And this is the JWST NearCam field of view. So this camera is really designed to go wide and not quite as deep as other cameras. On the other hand, when you look at its capability compared to other surveys that are either trying to tackle some of the dark energy problem or also HST treasury programs, it's extremely capable. So you can see here that even though it's designed to be wide and shallow, it actually is able to go pretty deep and basically carry on the legacy of HST, but with a much larger field of view. In terms of exoplanet imaging, as I said, it's able to do high contrast imaging using this new coronagraph that's being developed at JPL. This just shows you a simulated image. The way the coronagraph works is by blocking out light from the central star and then using various optical techniques to enhance the contrast in the region around the star. This is a simulation that was done at JPL for the planet around 47 Ursa Majoris. And as I said, we'll be really tackling here planets that we already know about. The key thing for a coronagraph is the contrast, and this just shows you the contrast here against angular separation from the central star. And JPL think they can get a contrast curve that's somewhere in this region here. The limit is the dark blue line, and then this shaded area is the area they expect to be working in. And the planets they're planning to tackle are these ones here. So this is really interesting. It's a significant advance from what we can do now with ground-based surveys. And this red line here is what we expect ELT will be able to do in the middle of the next decade. But one thing that we can't do, even with this technique, is address the issue of small rocky planets where we might want to look for life. So what I'm going to do now is transition to the question of the search for life. And I want to make the point that the WFIRST coronagraph will really provide a science and technical foundation for future missions that could do this search for life. So you heard from Kathy that this large ultraviolet telescope is one concept that's being proposed for doing this observation. The search for life is one of these questions that is one of the most compelling questions in astronomy right now. It captures the imagination of the public. So there's a lot of interest in this. Everybody's watched Star Trek or some science fiction program that addresses what life might be like on other planets. Most likely your kids have asked you, are we alone? Is there life out there? So it's an extremely compelling question, and we hope that this mission in the next decade or beyond will be able to answer that question. So how do we answer the question? Well, we think the answer is by studying biosignatures. And I should say that we're really talking about very small planets now, like Earth, and what we will be looking for as evidence of life are these spectral features. So ozone, oxygen, the water lines here, carbon dioxide and methane further out into the near infrared. So these are the kind of signatures that we will be looking for to provide us with some evidence that this particular planet may have life. Where would we look? Well, we would look in something called the habitable zone. Earth is in the habitable zone around its own star. This is the range of orbits where you can have liquid water on a planet. And if you go too far in and too close to the planet, like Venus, you are either very dry or you have a horrendous carbon dioxide atmosphere like Venus. If you go too far out, then everything's too cold and any liquids are frozen. So the habitable zone is this green region here. There are two different zones because, like everything else, astronomers can't quite agree on where it starts and where it ends. But for the sake of argument, it's this green zone here. And the other point this chart makes is that as you go towards late spectral type stars, which have lower temperatures, that habitable zone moves in, and then your planets are going around the star much more quickly. So So we would look in the habitable zone. One of the things that Kepler did for us is to start to give us a real good handle on the question, if I look at a given star, what's the probability that star will have an Earth-like planet in the habitable zone? And there's still a lot of work going on reducing the data from Kepler. We think WFIRST will help make the statistical data more solid, but it looks like that number's the order of 10 to 20%. One of the current papers that we've been using for our modeling is 0.16. So not a very large number. So the way you would find an Earth 2.0 is to do a survey of a pretty large number of stars in the hundreds. Some fraction of those, about 16%, might have planets in the habitable zone, and then some fraction of those would actually, when followed up with spectroscopic observations to look for these biomarkers, actually be Earth-like planets where you might have a better chance of doing long exposures to really look for these biosignatures. So it's a difficult problem. Now, one of the really interesting pieces of work that was done in the last year by one of our colleagues at Goddard, who's just moved to Space Telescope, Chris Stark, is to try and do modeling of the kind of yield you would get with different telescopes, making different assumptions about all the properties that we're learning about exoplanets and also the instrumental characteristics we would need to use. And the bottom line from his work is that if you want to do a survey to get a significant number of planets so that you have a good chance of finding a small number of planets that might have life on them, you've got to start with several hundred planets, and you need a large telescope aperture of the order of 12 meters or larger. So we have a really compelling argument here that to do this problem you need a very large telescope aperture. The other thing you need to do is go even beyond the contrast that WFIRST is achieving in order to be able to see these very small rocky planets that are extremely close to their parent stars. So you need at least another order of magnitude in contrast suppression to be able to get to that kind of sensitivity. And in order to do that, you need sort of tens of picometer stability on your coronagraph and optical system. So this is a really challenging problem, and it's not going to be easy to solve. The other point I wanted to make is that a 12-meter telescope also has a lot of appeal to the general astrophysics community. One of the interesting things is that when you get to that size of aperture, you can basically resolve 100 parsecs anywhere in the universe, and that just happens to be the kind of scale of star formation in galaxies. So you can really start to study some of these other questions in great detail that Kathy mentioned in talking about the Great Observatories 2.0. And this just shows the scale of different systems from star-forming regions all the way down to solar systems and then distances here. So with a large 12-meter plus telescope, we can start to make really big leaps in capability for general astrophysics as well. So how will we do this? Well, we have a group at Goddard that's been working with the Jet Propulsion Lab, the Marshall Space Flight Center, and with the Space Telescope Science Institute, trying to sort of look at what kind of technologies and what kind of approaches would work in making such a telescope a reality. And this is the kind of architecture that we've come up with. Very large 10 to 12 meter aperture. It will be a segmented primary mirror. We would have active thermal control. We'd use a sun shield as a sort of thermal sink. And the telescope would be mounted on this 6-degree of freedom gimbal to allow it to be pointed. And you have a number of options for how you get it there. You can fold it up and deploy it much like JWST, or you could even consider assembly in orbit. So there's a lot of options there. The other thing that we think is very important is that if you're going to try to do this, you really need to leverage what you already know. And we spent, as John said, a large amount of time on JWST learning a lot of new technologies, building a lot of infrastructure that's now available. And I've put them here, and this just summarizes some of them. So we've done a lot of work on integration and test, very high-speed interferometric testing that allows you to measure mirror segments down to picometer levels. Segmented mirrors, we've just done some experiments in collaboration with some partners on a ULE mirror segment, and we think with active stability control, active thermal control, we can achieve the required stability to be able to get picometer level performance out of these mirrors. Deployment mechanisms, we've got a whole swath of different mechanisms now that have been developed for JWST. We figured out how to do large sun shields and large deployable sun shields. We now have a chamber down in Texas at the Johnson Space Flight Center that could handle such a telescope for the integration and test. And we've learned a lot about how to build very stable composite structures for mirror backplanes. So there's a lot of heritage there we can start with, which makes the journey to get this to a reality a lot easier. So I will just finish up by summarizing, and I think on the cusp we have WFIRST, which is the next big mission from NASA and will allow us to really get a handle on the nature of dark energy. And then hopefully beyond that, we can start thinking about the search for life and a telescope dedicated to solving this problem. And as Kathy said, it is the golden age of astrophysics. So I just put this chart in here from John Grunsfeld. And that really does show you that both for doing dark energy observations and for exoplanets, we have a really nice set of missions that have got us to where we are today. And just to finish up, a lot of what I've said has been echoed in the New Worlds, New Horizons Decadal Survey and the 30-year roadmap that you already heard about. And in addition, there's an independent study that's been looking at this problem by the AURA committee, and that will be coming out very soon, and that's called Beyond JWST. So look for that as well. Thank you.
Dr. Alexey Vikhlinin is a senior astrophysicist at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, and Deputy Associate Director of the High Energy Astrophysics Division of the Harvard-Smithsonian Center for Astrophysics. After receiving his PhD in Moscow in 1995, Alexey came to the United States, where his main research is on X-ray studies of galaxy clusters and their application for cosmology and the physics of the intergalactic medium. He was recently co-awarded the 2008 Rossi Prize from the American Astronomical Society for his work on cluster cosmology and cold fronts.
Thank you very much. It's a pleasure to be here. I'd like to talk about next big strategic steps in the field of X-ray astronomy. And as a general remark, I'd like to say that if in the past couple of decades astronomers learned something, it is that to really understand complex phenomena, we need to observe in different wavelengths. From combination of this observation, we can really nail down the solutions of these problems. X-ray data are critical for some of the most fundamental astrophysical problems often in unexpected kind of ways. So I will discuss a couple of themes first, and these themes will provide a nice demonstration of where our field needs to go. So our universe is the universe of galaxies. These beautiful spirals and spheroids are basic building blocks of the universe, and also the sites where diffuse gas turns into stars, planets, and intelligent beings. So as astronomers, we strive to understand how these beautiful galaxies emerge from almost shapeless and formless initial conditions. And we know these initial conditions essentially through direct observations of the cosmic microwave background. That's the latest map from the Planck satellite. So the big question is how we know the initial state and we know the present state. It is what happened in between. That's the one of the greatest quests in astronomy. So now we have a very plausible theoretical framework. That's just another computer simulated movie of evolution of the universe with 10 billion years compressed into 1 minute. So the theoretical framework is that growth of structures and growth of galaxies is driven by gravitational instabilities, and the essential element of that framework is also that large amounts of energy are generated within the galaxies as they grow. And so you see those explosions and you see gas being expelled from the galaxies. For models to make realistic galaxies, the energy injection is vast. So roughly 50% or more of the baryons, which is supposed to be within the galaxies, gets ejected. Just pause for a second and think about it. You can look up the sky, you can see a Milky Way, you think it's a safe haven, yet in the process of formation of the Milky Way, a Milky Way worth of star material was ejected to the outside of our galaxy. So what is the source of this energy and how exactly it was ejected? It's obviously a fundamental and just daunting problem. So the next slide shows a predicted distribution of gas at different temperature regimes around those galaxies, and this gives us a hint where we might search for solution to this problem. So on the left, click the wrong button. On the left, we look at the distribution of very cold gas. So it's essentially starlight. That's what you see with the optical infrared telescope, and indeed you see a spiral galaxy. In the middle panel, you see the distribution of gas heated to above 1 million degrees. This is the gas that you see in the X-rays. You see a big halo with scales of almost 500,000 light years. This is the gas that was ejected from the forming galaxy. This is the site where the energy generated in this galaxy is deposited. By mass, they are roughly comparable. This is what you need to see to really establish and really constrain all kinds of theoretical ideas about the energy injection mechanism. Also, I would remark that looking at a picture like this, it's pretty obvious that you cannot understand the process of forming those galaxies without looking at different phases of gas around those objects. So you need essentially multi-wavelength observations to really understand it. So do we see these X-ray halos around galaxies? So if I would show you the state-of-the-art Chandra image of that emission, you would laugh me out of the room. It's basically just above the statistical noise. So to really do it, we need a couple of orders of magnitude improvement over the current capabilities, about 2 orders of magnitude improvement. If we zoom inside the galaxies, that's my second theme. If we zoom inside every big galaxy, we find a supermassive black hole in it. So this supermassive black holes sit there, slowly grow, and occasionally generate enormous amount of energy. And we observe this energy, active states of the black holes in different wavelengths. I show a couple of X-ray images. So gas is being pushed away, jets are generated on the scale of the entire galaxy, etc., etc. So these are the coolest objects in the universe, and coolest is not meaning the lowest temperature objects in the universe. And also they are critical for theoretical understanding is that they are critical, they play a central role in the formation and evolution of those galaxies. And because material moves at very high speeds around black holes, you typically generate very high energy emission from the vicinity. So you can say that they are X-ray objects. This is very well demonstrated by a comparison of an image of a very distant black hole in the optical and X-ray bands. So optical on the left, X-ray on the right. This black hole is very, very faint source in the optical, and it's about the only source in the same area in the X-rays. The largest mystery, though, for these black holes is that they exist at very large masses very early on in the evolution of the universe. This particular one shines when the universe was only 900 million years old, and it had a mass of over 1 billion solar masses. There's barely or not enough time for such massive black holes to grow since the Big Bang. By that point in the evolution of the universe. So can we see the most direct way to establish where these black holes come from? Obviously, is to detect the very early stages of their evolution, to detect their seeds at very high distances. What do we need to do? We need a couple of orders of magnitude improvement capability to over the current state of the art to be able to see the seeds of these supermassive black holes. So I guess I've made my point very, very clear. We need a couple of orders of magnitude improvement capability. Does it mean we need 100 times bigger structure? To understand that, we need to review what the current state of the art is. Current state of the art is Chandra X-ray Observatory. It's a technological marvel. It features some of the best mirror surfaces humanity ever produced. Okay, it was operating flawlessly for 15 years on orbit without any kind of servicing, etc. It did an amazing range of science from constraining equation of state in the neutron stars to detecting effects of dark energy on the growth of cosmic structures. What's most amazing to me is that this technological marvel has an effective area of 1,000 square centimeters. 1,000 square centimeters sounds like a big number, but in fact it's effective area of the 19th century great refractor in Harvard. This is a view from my office window. This is, those of you who have backyard amateur telescopes probably have that effective area. You wouldn't imagine doing dark energy and neutron star equation of state with your backyard telescope, but it's possible to do it with X-rays. So in a sense, we have a pretty low starting point to improve upon. So to build effective area 100 times Chandra's doesn't require 100 times more massive structure. You really can do it on a spacecraft which is approximately Chandra sized. So the path to build a Chandra successor seems pretty straightforward. You can take a Chandra X-ray observatory and essentially replace its mirror system with a new, smartly built mirror system, which even can have lower mass. Similar angular resolution would be fine. Same focal length. You can pack a lot more effective area in approximately the same size envelope. And of course, you can replace the detector plane with next generation detectors, which would feature advanced imagers and advanced spectrometers. So the heart of the concept, the heart of this progress would be how we build a mirror system. The reason the effective area is small for X-ray telescopes is that you can only reflect X-rays in grazing incidents. So you need to build nested structures which are long, and they used to have to be massive. So Chandra mirrors are glass shells of 1 inch thick. So they are polished incredibly precisely, but they are big and heavy structures. They weigh 1.5 tons to provide 0.08 square meters of effective area. So what we need to do is to be able to essentially pack the same input aperture with a lot more nested shells. This is becoming possible technologically, and this can be done through a modular, scalable design where you put a large number of thin glass shells with the thickness of the glass approximately used on your computer screens. Okay, and you can put them in modules, and you can build a bigger mirror from those modules. So there are several groups in the country who work on technologies that would be applicable for building these very precise thin glass shells. It's a wide range of ideas. Some feature introducing active control, so you can in fact control the shape of the mirror on larger scales with thin piezo film deposited right on the shells, and these active elements can have integrated electronics, devices that report the shape of your mirror in flight and the temperature of your mirror in flight very precisely, all done on a 1 micron type film deposited on the back surface of the mirror. So the expected performance gains when we are able to build this structure are very big. So a factor of 30 more effective area than Chandra can be combined with big improvements in quantum efficiency of the new generation detectors. A factor of 10 larger field of view for subarc second imaging because of better optical design for these mirrors. All in all, it's a factor of 500 gain in capability for searching for faint object or detecting very low surface brightness structures. So I'd just like to recap and say that when we're able to develop this technology to a practical point and build a successor for Chandra, then the science capabilities that will be opened are fantastic. You can start detecting black holes at very low mass range, at very, very early on in the evolution of the universe. You can say that it will nicely go together with Webb. Webb will detect first light in the universe, and this thing will detect first accretion light, accretion on the black holes that existed in these early galaxies. It will make tremendous contribution to our understanding of formation of galaxies because it can look at very low surface brightness structures. It can expose the cosmic web that exists at low redshift in emission by X-ray emission of the helium and hydrogen gas that fills those structures. Thank you.
Okay, I'd like to open it up now to questions. Okay.
First off, I'd like to thank everybody for the very informative talks. You've talked about a lot of telescopes that are currently being used and some that are in the design phase. Can you just give a rough estimate of the number of people involved in putting those telescopes together and approximately how long it takes?
Well, for the Webb telescope, is this on?
Is it on?
For the Webb telescope, it's about 1,000 FTEs currently working, and so that's huge. So added up over quite a few years, I guess at that level is probably roughly a 10-year project. So of order 10,000 FTEs just in the U.S. So, but it's the biggest one. One of the, say, the European extremely large telescope on the ground, they're figuring like €1 billion for that. So that tells you it's also a huge project. Maybe not as huge, but it's still huge. And worth it.
I'm just curious, for any of these telescopes that are working, like Chandra, Hubble, whatever, Spitzer even, once the data start flowing into your archives, is the bottleneck for getting results lack of astronomers or lack of funding or lack of coordination or what?
Alexey, you wanted to comment on that?
So I can comment on what's happening with Chandra. The Science Center recently did a study of what happens with the data. I think almost 80% of data gets published within 2 years of observation, and it's roughly split 50-50 between the astronomers who actually did observation and then those who analyzed the archive data. So given the number of projects that astronomers usually work on in parallel, I think it's not an unreasonable delay. So for X-rays, there's really no bottleneck.
I have what's probably a simple astrophysics question. There was a depiction in one of the presentations of a supermassive black hole at the center of a galaxy. My understanding of black holes is they're literally singularities, and yet it seems like the larger they get, the bigger the diameter gets. How does this all work? Is a supermassive black hole truly large, or what determines the size of a black hole? Not mass, but the diameter.
Over to you, Alexey.
I put this picture. That obviously was an artistic drawing. I took it from Discover magazine. What's usually pictured is the surface of event horizon. That's the surface beneath which the light does not go out. But this surface also has more practical physical means. If you look at the black holes from the outside, for example, the surface appears as superconducting surface. So, for example, if you can follow magnetic lines that go inside the black holes, they terminate at the event horizon. So, if you have material, following magnetic lines, large fraction of that material would look like it goes very close to the event horizon and then out. So, if you try to look at the light from the galaxy with the black hole with really, really high resolution, you expect strong gravitational distortions near the event horizon. So you expect to see a hole and a glow around it. So you don't really look inside the black hole, and you really don't look, at the singularity. But those pictures are, I'd say, to some approximate orders, they have some relation to reality.
I have a question about the X-ray telescope. So the next generation of Chandra that you're talking about, how does that compare to Athena that ESA is proposing?
Okay, very good question. So one thing that I didn't mention was, if you look at Chandra, I concentrated on the aspect of where it lacks capability, and that aspect was small effective area. The other aspect where Chandra lacks is really almost none of the high-resolution spectroscopic capabilities. And for astronomy became astrophysics when people started doing spectroscopy in addition to imaging, right? So there was a school of thought, and it's very I think it's very well-founded argument that after Chandra, what you need to do is a high spectral resolution observatory. So the idea was floated in late 1990s that essentially you need to fly a light bucket with a spectrometer that doesn't necessarily produce sharp images, but it can take spectra of bright sources and do very detailed spectra. So ultimately, the realization of that idea is Athena. So Athena will have a factor of 10 worse angular resolution than Chandra. So it won't be able to look at sharp images, to produce sharp images like Chandra does. It won't even be able to detect sources as faint because the sources will start to be confused. But it will be tremendous for studying spectroscopy of relatively bright nearby objects, and there's a lot of good science for that.
Several of you talked about the search for life in the universe, which is, of course, an incredibly exciting topic probably to everybody in this room. And in fact, some of the cave paintings that have been found in South Africa indicate that people have been looking up at the night skies, our ancestors, for maybe 200,000 years. That's 10,000 generations. There are 3 generations in this room. I personally find it absolutely phenomenal to be alive at the time in our species history when we finally have the tools to seek out, the answer to that question. It's just amazing to be part of this venture. Personally, my passion is seeking signs of life in the solar system, Europa, Mars, and so forth. And you guys have mostly talked about seeking signs of life outside the solar system, which is equally phenomenal. I wondered if you might reflect philosophically, maybe John, you led this off, about how these 2 different approaches to looking for evidence of life complement each other, merge, or whatever.
Okay, I'm thrilled with both possibilities. And as you probably know, we have laboratories at Goddard where we build instruments that are running around on Mars, digging up dirt and analyzing the chemistry. So the possibility of discovering life in the solar system is extremely exciting. It's the only possibility that we have to find out how it might really work if it's there. The possibility of finding remote life on exoplanets is there, but what the primary evidence will be oxygen. And so we won't know whether it does it by photosynthesis our way or some other way. So we can't do remote chemistry in any way that we've thought of yet. So if we can find it close to home, it's absolutely very informative in a way that nothing we can do remotely is informative. But the remote possibility tells us whether it's common or rare. Are we the only planet? Is this likely to be the only planet because of some special circumstances that could possibly support life, or is life common?
I think that'll be a great way to end this session. Thank you all.